Hi everyone, my name is Kathy Johnson. I am a modeler at Jacobs and I've been doing it for about 6 years. My experience has been with a variety of different types of modeling, including 1D, 2D, and 1D, 2D linked models for a range of applications and for different clients, including national government, local authorities, and many others. Ben, would you like to introduce yourself?
I'm Ben Watson. I'm a senior modeler with Jacobs. I've been Jacobs just over 5 years. I've got a very similar background to Kathy, really, working on a range of 1D and 1D, 2D modeling, mostly using Fluid Modeler. And I've also worked a bit with the Fluid Modeler team on some training and benchmarking as well.
Okay. Okay, so before we get going, we're both going to give you a bit of context as to why direct rainfall modeling is useful and important. And then I will then talk about what is needed to model flooding from direct rainfall and show you a demonstration of how to do this in Flood Modeler. And then Ben will then talk you through drainage modeling and its value, and we'll also do a demonstration by adding the drainage network to the model that I would have showed you. And then after that, we will have some time for questions and answers. Okay, so today's webinar is about flooding due to extreme weather. And I think it's safe to say that we're experiencing more extreme weather events globally. These are some of the parts of the world that have made the news because of flooding. And I know that today we have an audience from all around the world and listening in, so you might have seen some of these events firsthand. A lot of it is due to extremely high rainfall with an added complication, like an example of New York with the lower network capacity caused a lot of problems. In Romania, there was added flash flooding because of the huge amount of rainfall. Atlantic City had coastal flooding. Libya and Greece were big headlines because of the catastrophic damage to infrastructure caused by the storms, and in Hong Kong, landslides as well. But I do think that flooding due to rainfall is a global problem, and there's places that are experiencing it that don't make it onto the headlines sometimes. Like in East Africa, we had about 58,000 people displaced because of flooding. You know, Italy, Yemen, and this is all from Flood List, which tries to list all the floods occurring in the world. It's based on the European Space Program's satellite. So yeah, I do think it really is a global problem and affects us all. Here in the UK, I'm based in the UK, as is Ben and Adam. We've already experienced 3 storms in our sort of storm season, with unfortunately a lot of damage to properties and injuries and loss of life. And here are some images from the news in the UK. And it's clear that the frequency and the intensity of these storms is increasing in the UK and around the world. The UK Met Office recently reported that over the last few years, the increase is huge. 6 of the last 10 wettest years have occurred after 1998, and that's measuring from 1862. And the last sort of 10 years was 9% wetter than the previous 30 years, mostly in the northwest of England and Scotland. And we're also seeing that more extreme flooding is occurring within cities and towns where fluvial risk isn't really the problem. And the flooding has been due to subsurface drainage systems reaching capacity and then surcharging, causing excessive damage. And I'm also finding that flooding is starting to affect everyone on an individual level in small and big ways. I myself am starting to see roads around my house saying these roads are prone to flooding due to high rainfall. There's a park that I live near, and it's got a huge puddle that my daughter loves jumping in, and every year that puddle gets bigger. In fact, this year she was a bit too scared to jump into it. So overall, it is becoming more important and urgent to design living areas with measures for extreme flooding. And a good starting point is having the knowledge of the area as well as the rainfall that it experiences, and then using that to extrapolate for future events and protect against them. So let's talk about how we can model flooding from direct rainfall. or pluvial flooding. So the first question is, why do we even need direct rainfall modeling? Direct rainfall modeling is very different to modeling flooding from single sources because it is a distributed source. It also means that even areas that are isolated from water bodies or sources can get flooded quickly and cause new flow routes, which is especially hard to predict in urban areas. In fact, because of the small spatial and temporal scales at which this type of flooding generally occurs, it makes it more difficult to predict and pinpoint than sort of typical single source flooding. And that is one of the main reasons direct rainfall modeling is required. In some cases, it's the only way to get reliably accurate data about flooding in an area. Another aspect to consider is when you have non-standard catchments, maybe something that's highly permeable or very small, or a catchment that's about to change. Perhaps buildings is going to be urbanized and there's going to be buildings on it. And also lots of natural flood management measures are starting to be implemented. For example, in this image here in Scotland, they've used higher infiltration upstream of a channel to reduce flooding downstream. And so these kinds of scenarios are only really, it's only possible to get accurate results with direct rainfall modeling. And there's loads of other reasons, forecasting and emergency responses and more. So if you do decide to go with a direct rainfall modeling, these are some of the things to consider. Firstly, where is the rainfall data going to come from? Is it observed data? Perhaps you might have a gauge in the catchment that you could use. Even so, always make sure that it represents your catchment well and isn't a point of extreme rainfall or the opposite. Or you could use a design rainfall event, for example, a 1 in 100-year storm with a certain storm duration. And this is normally calculated using an intensity duration frequency curve, which in the UK we use something called the FEH flood estimation handbook, sorry. And what that does is it gives you a depth of rainfall based on the probability and intensity of the rainfall. Or you may even have probabilistic data that you could use. So once you've got that, say you decided to use a design event, then you have to figure out how is this depth of rainfall distributed in time and space. For design rainfall, usually a trapezoidal distribution curve is used, like this one shown on the right. And normally for large catchments, you might need to apply different rainfall storm durations and depths in different areas because it won't necessarily be the same over such a large area. Another thing to consider is your infiltration, because not all the rain falling will cause flooding. Some of it will be absorbed by the ground, or if it's impermeable, it might be through cracks or tree cover. And you can model this, and this is useful when you have variations in the ground and ground cover. In Flood Modeler, you can do this using the green amped method, which basically changes the rate of infiltration with time based on what type of ground you have. And you can get the various soil types in areas through master map data in the UK. And there might be similar databases where you are, where you can get that data from and apply it. Or if it's a really simple model, you could just take it out of the rainfall and keep it simple. Another thing to consider is base flow. This is the portion of flow that happens after the rainfall event and before the next one. This is more significant in larger catchments. Sorry about that. This is more significant in larger catchments. Another thing to consider as well is your topography. Make sure you've captured anything that could act as an embankment or that could move flows around. For example, a culvert. Buildings are very important because they can change flow routes. So that needs to be captured accurately to get good data. Another thing is the drainage network. This is important because drainage networks can move flows around catchments to areas that water may not necessarily go to. And Ben will explain more about this in detail when he talks about the drainage system. Okay, so now we will go to a demonstration of how to model a 2D direct rainfall model. And as I go through it, I'll be doing this on Flood Modeler. And as I go through it, I'll try and show you some features that Flood Modeler has that can help you. Okay. Right, so here we've got Flood Modeler. This is what it looks like. Here in the middle is where you have your GIS workspace. This is where you get to see all your layers. On the left here, you've got all the files that are associated with your simulation. So if you had a river network or event data or an urban network, these files would appear here. On the bottom here, you've got all the layers, which I've loaded to save some time, and I'll show you them in a minute for our model. On this side, you've got your 1D river network information and initial conditions. And at the top here, you've got a number of tabs that help you build your model. You've got some hydrology data there, and you can even view results from here. Okay, so what I'll do is show you where we are. So we've got some mapping here. So we're in this area here. That's my LiDAR data that I'm going to be using for this demonstration. I'll keep it off at the moment, and I'll show you what my 2D simulation window looks like. Okay, so this is what it looks like. It's very simple to use because all you have to do is fill in a lot of these spaces. So here we've got the name. We've got the duration of how I want how long I want to run this simulation for. You can run to steady state or the various different ways that you can run this. If you had a river network, you could include that, and it would create this tab, which will allow you to put in all the information about that in there. You've also got two different solvers that you could use. The GPU solver, if you've got the capability with your computer, is a lot faster. So if you've got a large run, it would be very useful to use something like the GPU solver. So once you fill that in, you can go to the domain area, and here, again, at this top area shows you the domain. In this case, I have one domain, but you could have multiple domains and use different solvers for them. You've also got this area where you introduce your topography. So in this case, I've got my DTM, and that it's very simple to put it in. All you do is drag and drop, and you'll have it there. But if you had other layers, like for example, if you wanted to reinforce any embankments or roads, things like that, you could add those in, and it will read those on top of the previous layer. I've also got my grid size of 2 meters and a time step of 1 second. And I've also created an active area. So the active area tells you which part of the grid is going to be solved by the solver. So in my case, I've got one already created here. So that's going to be my active area. Let me move this across so we can see. So that's my active area, but it's also very easy to create the active area in here. You don't have to have it preloaded. So I'll show you just an example. So if you wanted to create it in Flood Modeler, you could go to 2D build, and I'll just call this ride 1. And it will add that layer here in my layers, and then it will create this tab that I can use to edit. So here I will just create a new polygon, and there you go. And it's that simple to create your polygon. You also have the ability to snap it to, if you had certain layers you wanted to snap that to. Okay, so for now I will just remove this because we don't need it. Stop editing. Okay. So yeah, I've got mine already preloaded here. Then you can also put a default roughness, but there's different ways you can also read roughness. In my case, I've got an ASCII file that has my Mannings and roughness for buildings, roads, grass, cover, and all the different types of land use. But if you had something that had maybe like a feature code, you could also use a lookup table to show what the Mannings N is for each of those codes. Then we've got the boundary condition. Again, you can draw this in directly in Flood Modeler using the boundary line. In my case, I've got mine preloaded here. So I've snapped it to my polygon, and that's this is for me in this case is a normal depth boundary. But again, you could have different boundaries. You could have an inflow, outflow, a HT boundary or water level boundary. And I put a slope here for what I would like for my model. In terms of rainfall, I've created 3 polygons where I'm going to have different rainfall information. So I'll show you one of those. So here I've got my shapefile, I've got my rainfall units, and I've put them in directly here, but you could easily just read that from a hydrology unit file or an Excel sheet using the time series file. You also have the ability to put, in my case, it's rainfall only, so it's net rainfall and the infiltration has been taken out of the model, but you could quite easily use rainfall and spatial loss. And like I said before, you can use the greenamped method in Flood Modeler and put some shape files in and a lookup file and if you have master map data or equivalent, you could put that in here as well. Okay, then I don't have any 1D structures yet, so that's fine. Outputs, again, you can create grids. So I've got a few of the things that I want as a grid, but you could also add time series data. So if I wanted to have a time series of a certain location, I can put that in here and it will record that data, and you can tell it how often you want it to record that. Also, you can put flow lines. So if you want to know flow across a certain road or a flow path, you can draw in a line with a shapefile and it will read that for you. You also have in this options tab the ability to choose the different solvers. So there's 4 different solvers that Flood Modeler has, and there's more information about that on the website. You can use the different types of precision, and you can also change some of the default values that are used. And once you've done all that and you're happy with your simulation, you simply press run. I'm not going to do that right now, and you'll be able to see the window it creates when Ben does his presentation. But basically, it will create a diagnostic window when you can watch your run and see how it's doing. So I'm going to close that for now. Oh. And I'm going to load my results so you can see what they look like. Should load up in a minute. So typically with a rainfall model, you'll see this sort of image where every single cell is covered in water, which is quite normal. So the way I like to view it is I like to remove the, I like to make it transparent as well so I can see the roads that are causing flow paths. And then I'm going to say that for me, 30 millimeters is okay and don't need to view any of that, and anything above 0.5 meter, for example, is in red. Oh, let's put it red. And then you say generate, and if I say okay, you'll be able to see the flow paths a lot clearer. I'll turn the flow lines off for a minute. So you can see generally that my flow is generally following this flow path seems to be the big one. And it doesn't seem to be too much ponding, so I've got my boundary line in the right place and maybe at the right gradient. And if you zoom in a bit closer, you can see in more detail what it looks like and which properties are affected and so on. So that's just a general quick tour view of how you can do a quick direct rainfall model on Flood Modeler once you have all the data. And now I'll pass on to Ben for his part of the presentation. Thank you.
Thanks, Kathy. Okay, hopefully you can see my screen now. So, as Kathy has explained and demonstrated, intense heavy rain in urban areas often results in pluvial or surface water flooding. And Flood Modeler's 2D solver is an efficient solution for producing detailed direct rainfall models that can simulate this pluvial flood risk and identify surface water flow paths within urban areas. But what if the problem is more complex than a simple accumulation of rainfall? What if we consider the influence of the urban drainage network on flooding in urban areas? So just to provide some context of the importance of drainage networks, I've provided a couple of quotes here from UK authorities that really highlight why drainage networks should be considered when trying to model extreme rainfall events in urban areas. The first quote is from the UK Minister of Environment, and it states that our traditional drainage systems are under increasing pressure from the effects of climate change, urbanisation, and a growing population. The second is from one of our lead local flood authorities in the UK, and it states that a sudden storm or downpour can often result in more water on the road than our gullies or drainage ditches can cope with. In severe weather, the capacity of the drainage system can be overwhelmed by the amount of water trying to run off from the road, and flooding can occur. These two quotes really highlight that there is an issue with urban drainage networks when considering flooding to urban areas, and with climate change, this issue is likely to get worse. So why do we need to consider the drainage network? There's three things really in the ways we need to consider the drainage network. The first one is that the network can act as a source of flooding, mainly via manhole surcharging in urban areas, like the photo shown on the right-hand side of the slide there. Secondly, the network might act to alleviate flooding. So the stormwater network, or in some cases a combined network, is intended to act as a drainage system, and surface water flow paths are intercepted by drainage structures such as road gullies. Then finally, there are often complex dynamic interactions happening within an urban catchment that need to be understood. The drainage network has the ability to interact with surface water at manholes and gullies, with river channels or fluvial flooding at outfalls or sewer overflows, and in some cases it can actually interact with tidal systems if outfalling into a tidal water body. So we know why we need to consider. How do we actually consider the drainage network when modelling these extreme rainfall events in urban areas? And there's a few different methods we can use based on the complexity of the representation that you require. So the first is a very simple consideration of network capacity. This is appropriate if you're not concerned with the network acting as a source of flooding. You know there's an existing network and you have an idea of its capacity. You could then simply remove that capacity from the gross rainfall hydrograph. So an example of this is we know there's a network and we know it has a 20-year, in terms of return period, capacity, and we then deduct the 20-year hydrograph from all higher magnitude return period events. Or we might simply represent that as a drainage removal rate expressed in millimeters per hour. The second method, and this could be combined with the first in some cases, is appropriate if you know where flows are exiting your drainage network, for example, at a river outfall, and you simply want to understand the impact of that contribution on flooding downstream. And in that case, you'd simply apply the outfall time series, so the flow time series coming out of your network at the outfall. You'd apply that as an inflow boundary to your 1D river model, for example, and that would show that kind of knock-on effect of the outfall into the next system. If you're interested in a detailed assessment of flooding in an urban area, you want to limit the assumptions made regarding the network capacity and truly understand the interactions between the surface, the network, and possibly a connecting river or tidal system, an explicit representation of the network would be the best option. So what does that actually involve? Explicit representation of the system. The modelling of drainage networks involves modelling of the complex network of pipes, manholes, and structures. So examples of structures could be weirs within the network, pumps, or tanks. all as 1D model components. So similarly to 1D river modeling, flow conveyance through the network is then simulated once inflow and outflow boundaries have been added. Within urban areas, this then allows us to obtain a detailed understanding of the key issues in the network that we've touched on. So these would be things like pipe capacity, points of flooding from manhole surcharge, and discharge via outfalls. We can then go on to link the 1D urban network to the surface, such as at manholes, and represent both the surface and subsurface flows and the interaction between the two to get a better idea of runoff routing and key flood mechanisms related to the urban network. I'm going to go on to talk about how we do this in Flood Modeler, but all of this capability is available using Flood Modeler's 1D Urban Solver. And just to quickly cover what kind of opportunities this opens up in terms of modeling our urban areas, you can hopefully see that this opens up the possibility of fully integrated catchment modeling. So firstly, looking at the interaction between the network and the surface, we'd be looking at this kind of link. So the dynamic link between the 1D urban network and the 2D model domain. But we also have opportunities for links between the network and the river channel, and the river channel and the surface or floodplain. So just to quickly summarize what the 1D Urban Solver actually is before I go on to provide a demo. And I'm just going to focus on some key points in this slide, really. The 1D Urban Solver is derived from the US Environmental Protection Agency's SWIM software. So anyone that's familiar with SWIM will be able to pick up the 1D Urban Solver really quickly and efficiently. The SWIM engine is widely used. It's an industry standard across the world, and it's very robust. The 1D Urban Solver is a fully hydrodynamic flow and level simulator for drainage network systems. This means the software will essentially simulate time-varying hydraulic results. So things we might be interested in are flow, velocity, and level within the network, and throughout the period of the simulation as well. The 1D Urban Solver has been developed to be intuitive and easy to use. So even if you are new to 1D drainage network modeling, you'll be able to pick this up really quickly, particularly through the use of our Getting Started guides and the training courses that we offer. It's important to note that the 1D Urban Solver allows detailed modeling of very basic systems. So that might be a single branch of a network like this, to very complex multiple branch systems with multiple interconnections and branches like we often see in urban areas. And then just to finish off a summary on the 1D Urban Solver, we've recently benchmarked the 1D Urban Solver against other software with drainage network modeling capabilities. And we found the 1D Urban Solver was up to 49% faster while providing very similar results, so a close comparison in results compared to the other software. And the results of that benchmarking study are available on our website. Okay, so I'm going to jump over to Flood Modeler and just provide a little bit of a demonstration. So I'm starting here with the 2D model and results that Kathy demonstrated for us previously. Now, if I turn off the DTM and the results for a second, we can see the catchment is heavily urbanized. There's the usual kind of mix of residential and non-residential properties, and then also a network of roads within the catchment as well. And what we've failed to consider so far is the influence of the drainage network on flooding in the catchment, and I'm going to do that now. So firstly, I'm going to open an existing 1D urban network. I'm going to do that by just going up to the 1D urban build tab and selecting load. I'm just going to grab the IMP file, so that's the urban network file there. You see that'll open up. So I just want to point out here that it is very easy to build 1D urban networks from scratch in Flood Modeler. This model you can see is fairly complex. It took me a couple of hours to build. And as long as the data is available to us, anyone could do a model build from scratch using the very simple steps and use of the many automated tools that we have available. These are things like the model defaults options, and also the multi-edit view table, which I'll come back to just a bit later in the demo. But for the purposes of this demonstration, I'm just going to focus on taking an existing model and getting it to the point where we can link it to the 2D model that Kathy has already made for us. So just quickly looking at the existing model that we have, you can see the network is made up of a series of nodes or junctions that define our manholes. We've got links or conduits defining our pipes. We've got subcatchments. So if you're familiar with drainage network modeling, you'll be familiar with the subcatchment approach. Basically, each subcatchment defines the rainfall runoff assumptions associated with these discrete areas of the catchment. Those flows or the runoff from the subcatchment are then applied directly to corresponding manholes within the system. Then finally, this model has 3 rainfall hydrographs. Very similar to the way Kathy was applying before, we've got a rainfall time series, only this time they're being applied directly to the subcatchments so that the subcatchments can calculate those rainfall runoff losses. We can do some quick inspections of the network. So starting with the nodes, we can just double click on them. So if I want to have a look at that node there, I'll just make this a bit bigger. So there's not a load of fields to populate in terms of junctions. We can see we've got a node name, some coordinates that are automatically populated. You can apply inflows directly to your network. We haven't done in this case because we've got the subcatchments. And we also define the invert elevation. So it's important to note there that the inverts within your system are firstly controlled by the junction invert levels. The inverts in your conduits or pipes are then defined using an offset against the absolute level, and I'll show that in a minute. We've got a maximum depth to ground, and then we've also got some other parameters, particularly the ponded area, which I'll come back to when we create our links. So conduits, very similar, we can just double click, and we get the fields that make up the conduit parameters. You can see that we've got a circular shape, and if you just select that there and go on the menu, bring that across, you can see we've got a single circular barrel and we've got a 0.6 meter diameter. Other things that you might be used to seeing, so we've got length, roughness, we've got some entry and exit loss coefficients as well. If you want a more kind of visual representation of the system, you might want to plot a long section. So again, very easy to do so. If you just want to see from maybe an upstream node to a downstream node, you can just select the top of your system, right click and go to long section. That'll bring up something like this. So you can see how your network looks. And then if you want to look at a few different long sections all kind of in quick succession, what we can do is turn on the labels, and then you can just see which node you want to go from. So maybe we'll go from junction 30 here. We go back to our long section and just scroll in the list here to junction 30 and click plot. And you can very quickly get a kind of visualization of your network and maybe spot issues or get a better understanding of what's going on. Straight away there, I can see there's an adverse gradient, which is probably going to ring some alarm bells, whether that's real or not, whether there's an error in setting up the model, and those can quickly be corrected. What I'm really interested in here is adding the urban network into our existing 2D direct rainfall model. So firstly, I need to do something about these subcatchments. As I said before, the subcatchments represent the rainfall runoff assumptions in these polygons. We know that the direct rainfall model we're trying to link to that Kathy built for us before is dealing with rainfall and runoff explicitly. So we're just going to remove the subcatchments. I'll start by making a copy of my network. So I'm just going to right click and go to copy. I'll call this one 1D, 2D. And then we just want to make sure it's active. So the 1D, 2D network is active. Okay, so once we've made our copy, we then want to remove the subcatchments. We'll do that by going over to the 1D urban network table. So that's in the bottom right here. It's an option in your network tables. I'll just drop that out. And we're met with the nodes and the links menus. So I'm going to go for the nodes menu. And you can see we've got all our subcatchments and associated rain gauges grouped. And I just want to get rid of them all because we don't need them. So I'll select all of those, right click and delete. What we're then left with is a series of nodes and links that we can then link to our 2D model. So now we want to define those dynamic links between the 1D urban and the 2D domain. And as I said before, we're going to consider links between the 2D surface and the urban network at manholes within the system. So we firstly need to determine exactly which manholes we're going to link to that surface. You can see from that active area of the 2D model that there's 2 nodes that are outside our active area. We're not going to link nodes outside the active area because obviously they won't be linked to anything, so we don't want to select those, but we can link everything else, so all the junctions that are in there. Again, very easy to do. We're going to go up to the 1D Urban Build tab and select the 1D Urban 2D linking tool. That'll give us a new menu here, which basically defines the type of the link down the right-hand side, and also gives you the option of which nodes you want to actually link. So we can see from the labels, I don't want junction 1, I don't want junction 33, so we'll just select everything else. Once we've got them selected, we'll right-click and select Create 2D Linking for selected nodes. That's going to bring up this little menu here, where it'll give us the opportunity to either append to an existing shapefile or create a new linking shapefile. So I'll create a new one. Just call this 1D junction links. And then in the Advanced tab, we've got some options for changing the shape of the link, the dimension of the link. So you might be trying to link something bigger or smaller, and you want to change the actual size of the link accordingly. We've also then got a discharge coefficient and modular limit to control the flow equations in that 1D 2D linking. Okay, I'm just going to click OK on that. We can see it's brought up a new shapefile in the bottom left, and I'm just going to zoom in, and we can see each of the junctions that we've linked has now got a shapefile around it, and that defines the actual location of the link itself. So we've made the links, but before we go and actually dynamically link those simulations together, there is an important step we need to make, and that's the ponding settings associated with the nodes, and that controls the passing of volume between the 2 solvers. So firstly, we're going to go over to our network, right-click and go to Model Settings, and we need to ensure that the Allow Ponding is ticked on. That basically controls whether the 1D urban domain allows flow to come back into the network. So it's very important that we turn that on. And so we go for OK. Then secondly, we need to define a ponded area. So to help with those volume calculations, the 1D urban network needs to have an area above the node. You can do that like we looked at nodes before, so you can just double click them and manually edit the ponded area. But what's much more useful and quicker is the multi-edit view. So if we select that, that'll bring up a table of all of our nodes. So this isn't just for the ponded area, you can modify any of the parameters that way. But we're just going to change this one. So I'm going to select them all, right click and modify. Now, if you were paying attention before, you'll notice that Kathy had a grid resolution of 2 meters within the 2D model domain. We ideally want our ponded area to be consistent with the 2D grid size. This is specified as an area, so I'm going to change that to 4 meters squared. We'll check it's been applied correctly. Okay, save it and close. And then just to be safe, we're going to save the urban network at the top left there as well. So once we've done that, our 1D urban model is linked and ready to go. So we need to then create the dynamic link between the 2 simulations, and that's all done from the 2D simulation file itself. So if we go over to the 2D simulation file, I'm first going to make a copy of it. We'll call this the same name, but with 1D 2D afterwards. And I'm just going to open that up. So this is obviously the same simulation file that Kathy showed before. The only difference we need to make is the link to the 1D urban, and that's using this 1D linking option here. So if I just take this on and off, you can see it's bringing up the 1D urban links tab. I'll go over to there, and then it's just a simple case of drag and drop to link your simulations together. So we want to bring in our 1D, 2D IMP file. We want to bring in our 1D junction links. We'll save it, and we're going to set that running. What we're then met with is the same diagnostics window that you're probably used to from 1D river or 2D simulations, only this time we're given the 2D and the 1D urban tabs, and that'll give us the live runtime diagnostics as the simulation progresses. I'm just going to leave that running in the background, and instead we'll have a look at some results that I ran earlier. So again, this is the 1D maximum depths that Kathy was showing. We can play through a simulation. So we could look through the time steps of the simulation and see how the flooding progresses. And just click that forwards a few. So we can see we've got an accumulation of rainfall sort of in the center of the catchment here. And then as the flood event progresses, we should start to see the flow moving slowly towards the north of the catchment. So from initial inspection, the results look pretty similar to what Kathy showed before for the direct rainfall only. The difference we've got here is the fact that it's linked to the network. Because our network hasn't got any other inflow to it, it's purely just the direct rainfall being intercepted by the manholes, we should then see some flow in our system. So I'm just going to bring in the linked version of that network for the same results. Okay, I'll set that active. Okay, and we want to have a look at some flows in the system. So we've got an accumulation of flow in kind of this area. So we might want to look at flow through these pipes. Again, we just select them, right click, and this time I'm going to go for a time series. That'll bring up our kind of results window here, and I'm going to have a look at link flow. So we can see the flow through the system. You can click backwards and forwards between different conduits, see how the flow progresses. You can see where the main points of flow being taken into the system are and where it should increase and decrease. And then again, we can have a look at a long section. So if we want to go from here down to the outfall, we can just select the top node, have a look at a long section, and we can play the animation. So we can see the propagation of the flood event. You've got the flow entering the network, and you should see it receding again. So some really kind of useful visual inspections that we can do on our results. So just to summarize on what we've covered, across the world, we're seeing increased flooding due to extreme weather events, particularly in urban areas, resulting in flash flooding and risk to life. Direct rainfall modelling allows us to understand this issue and build detailed models representing urban flood risk and understand overland flow routes. Through the use of Flood Modeller's 2D solvers, we're able to quickly and efficiently get detailed model results to represent the issue. We can then combine multiple solvers within the Flood Modeller user interface to add more detail and accuracy to our modeling and explicitly represent the drainage network. With the right data, we're then able to represent these very real urban flood risk issues and go on to find solutions to mitigate against the problems.